Good morning, dear students. In the last class, we discussed about the image formation by the concave mirrors and also the uses of concave mirrors. So I told that is important for examination point of view for 2 marks. Any one of the diagram may ask. So here one more diagram, that is image formation by a convex mirrors. So in the last class, we discussed about the concave mirrors. So now we see about the convex mirrors. So what is this and in the concave mirrors there we learnt about around 5 different positions, right? The image formation by an a mirror by placing an object at 5 different positions, but here we have only two positions. We have only about two positions. So image formation by a convex mirror, we have only about two positions. One is at infinity and one is between what is it, between infinity and the pole. Between infinity and the pole only the two image will be formed. Suppose here in a ray of light, and the rules of ray of traveling, the ray travel rules, everything is same as that what we did in the concave mirrors. Okay, so now when an object is placed at infinity, so the two rays will fall like this. So this is one ray and here one ray is fall. So after reflection it will get reflect back like this. Okay, so it will not meet in it at any moment. So here when we uh, what is it, when we try to take the image, virtual image, so it is not a real image, it's a virtual image. Why? Because image is not formed, right? Okay, so it is get reflected back. So here at the focus f behind the mirror, so where the position of the image at the focus f and also behind the mirror, does it possible to find the image at behind the mirror? No, definitely not. And what is the size of the image? It is highly diminished point size. See, yeah, this is the AB is the object size. So see here the point size. So it is possible. Okay, so it is not possible. It's a virtual image and also it's a erect image. So next position is, so between infinity and the pole of the mirror, so between f and p, so the position of the image is between f and p. See, between f and p, that is, this is also virtual image and it is also diminished. See the object size, so it is ab, it's a bigger. So here see the object, here ab is smaller, so it's a highly diminished, so it is diminished one. And also is a virtual and erect image, there is no real image for this, is a virtual and erect image. Okay, so next next here, sign convention for reflection by spherical mirrors. Sign conventions. So what is the sign convention? So these are very important as a to solve the problems. Okay, so what is sign convention? So while dealing with the reflection of light by spherical mirror, we shall follow a set of sign conventions called a new Cartesian sign convention. So in this convention, the pole of the mirror is taken as the origin and the principal axis of the mirror is taken as the x-axis, and x-axis of the coordinate system. The conventions are as follows. The first one, the object is always placed to the left of the mirror. This implies that the light from the object falls on the mirror from the left hand side. So all the distance parallel to the principal axis are measured from the pole of the mirror. So all the distances measured to the right of the origin along the x-axis are taken as a positive, while those measuring to the left of the origin are taken as negative. So the distance perpendicular to the above the principal axis are taken as positive, and the measure perpendicular next distance measured perpendicular and below the principal axis are taken as negative. Okay, so I think you not understood, so I'll give one picture. I hope you'll understood there. So here this is the pole. So pole is considered as origin. So here this is a Cartesian system Cartesian system. We know Cartesian system, that is the coordinate geometry you learnt in your ninth grade and all in the mathematics. So the same thing here also, but what they tell in here, so we know that in the Cartesian system, so when we take this Cartesian system, this is what is this is y axis, this is y dash, and this is x axis, and this is x dash. We know that. So here all the signs are positive and positive, and here, so what is that? So one is x is negative and y is positive. So and here everything is negative, so x and y both are negative, and here this is plus. What is plus? So x is plus and y is minus. In the Cartesian system you learnt in your previous grade, in ninth grade in the mathematics. So here also they take the same concept and they make small changes in that. So what is the first point? The object always place it to the left of the mirror. So from the left side it has to place the mirror object. Okay, so your vertical height is taken as positive, we know that. So here this is the x axis. If it is x axis, so here we can take this as positive. So when you talk about y axis, it will take it as negative. See here, that direction towards the left is negative, isn't? So the direction, this is a height is taken as positive, and here also height downwards you can take it as negative. Why? Because if you take it as x axis and y axis, so that Cartesian system, so these are the sign convention we have. The same sign convention they took and they did small changes in that. All the distance measured to the right of the origin along the x axis are taken as positive, while those measured to the left of the origin along the y x axis are taken as negative. X axis are taken as negative. So this one, so towards this side it taken as, see, direction towards right is positive and direction towards left is negative. Next point here, direction measured perpendicular to the above principal axis. Above principal axis along y axis are taken as positive. Above principal axis, this is a principal axis, so above principal axis is positive, height upwards is positive, height downwards is negative. So next, the distance measured perpendicular to the below principal axis is taken as negative. This is negative, just now I explained. Okay, so based on this, the form that the problems we need to do. Okay, so just look into this sign conventions, so it's very easy also. So it is almost like a coordinate system. Okay, so next we'll move to the mirror formula. So here this is the mirror formula, and this is one of the important formula. Why? Because in this chapter only you're going to get the what is that, problems, and this chapter and one more chapter is electricity. Okay, so and the two chapters you're going to get the. So in a spherical mirror, the distance of the object from its pole is called the object distance. So these are some terminologies we should remember this. Okay, in a spherical mirror, the distance of the object from its pole is called the object distance, that is u. The distance of the image from the pole of a mirror is called the image distance, we can call that as v. Okay, object distance is called as u, and image distance we can call it as v. You already know that the distance of the principal focus from the pole, that is focal length, already you learned this focal length, that is f. So there is a relationship between these three quantities, so it is given by the mirror formula. Okay, this is known as the mirror formula. Okay, so this is mirror formula, that is 1 by v plus 1 by u is equal to 1 by f. This formula is valid in all situations for all the spherical mirrors for all positions of the object. You must have used the new Cartesian sign convention. Just now we learned this Cartesian sign convention. So use this Cartesian sign convention while substituting the numerical values of u, v, f and r. R is the radius of curvature in the mirror formula. Okay, for solving the problems. I hope all of you understood this. So this is the mirror formula, so keep this remember this properly, that is 1 by v plus 1 by u is equal to 1 by f, and even you can write here 1 by u plus 1 by v is equal to 1 by f. Okay, u v f, just remember like that, u v f. Okay, so just remember like that. Okay, so next is magnification. So what do you mean by magnification? So magnification is nothing but extending the object. It may be a zooming or it may be a de-zooming, mean in the sense it is extending. So just like this, I'll show you. Right, just a minute. here. So magnifying in the sense it may be something like this is here. I'm magnifying this image, so I'm zooming. So it is, see, I reduce the size of that. So magnification is come under the both, so it is reducing and also it is enlarging. So enlarging or reducing is known as magnification. Actually magnifying glasses are used to, I think you know, you're all familiar with the magnifying glasses. Why it is used? To see the object, to zoom the object. Okay, they use the magnifying glasses. So here also the magnification is same, is nothing but the same, that is zooming or what is that, particular image. So zooming the particular image like that. Magnification produced by a spherical mirror gives a relative extent to the to which the image of an object is magnified with respect to the object size. It is expressed as the ratio of the height of the image to the height of the object. It is usually represented by a letter m. So magnification is represented by a small letter m, So and also the formula for this is height of a image h dash by height of a image, height of a object, height of image, and height of object. So we can also write it as m is equals to magnification is equal to h dash by h. This is also one of the important formula. So okay, the magnification m is also related to the object distance u and also image distance v. It can be expressed as, so here image, height of image is nothing but object distance, so you can take it as magnification m, which is equals to h dash by h, which is equal to minus v by u. So you may note that the height of an object is taken to be positive, as usually it is placed above the principal axis, and the height of an image is taken as as positive for virtual image. However, it is to be taken as negative for real images. So only the taken here height of image is minus v. Okay, so u is the object distance, v is the image distance or image. Okay, so the positive sign is the value of magnification indicates that image is virtual. Is it clear? So this formulas you should remember to do the problems. So here this is one formula is 1 by v plus 1 by u is equal to 1 by f. This is one formula, and also here magnification, that is m, which is equal to h dash by h, or also we can write it as m is equals to minus v by u. So these are the important what is that, formulas. So in this chapter you have around 4 formulas. Okay, so in that 4 formulas only you're going to get the problems. 4 to 5 formulas we have come in the entire complete chapter. So already we learned one formula, r is equal to 1 by f. So that is one formula, and here 1 by u plus 1 by v is equal to 1 by f, that is one formula, and here m is equal to one formula, and 2 more formulas were there for the further you're going to get that. Okay, so based on these formulas only you're going to get the problems in the examinations. Okay, so be thorough with these formulas and list these formulas aside. So and see that what is I mean, this is mirror formula, right? Mirror formula, right, like this, and by heart like this, mirror formula. So mirror formula, so which is equals to 1 by v plus 1 by u is equals to 1 by f. So like this, so list of all the formulas whatever whichever they're in this chapter. So and you can by heart that, or you can remember by using any of the tricks which you know, which is familiar to you. Okay, so then it is very easy for you to solve the problems. So in the physics actually the problems are not much complicated, but we need to remember the formulas, and also you need to extract the data, I mean whatever they given in the question it properly. So you should remember, you should extract the, suppose in the question they give that some data, the what is the virtual image, the virtual image distance, real image distance, like that they given. So you should extract the data correctly from the problem. If you do that, and also if you write the data and the formula, so out of 3 marks you're going to get 1 or 1.5 marks there only. So the remaining 1.5 mark is for substitution and simplification, and the substitution and simplification is not much difficult here, it is very easy only. So basic substitution and simplification were there in this physics problems. Okay, so these are the 2 formulas you should remember and practice, and 2 more were there, so we'll discuss that 2 more what is the 2 more formulas. Okay, so learn this properly. See any doubts you have, so please message me or call me. Okay, so today in today's class we studied only about image formation by convex mirrors. So in the image formation by convex mirror we have only two what is the two positions. We'll take only two positions, but in the concave mirrors we took around six positions. So that is in that, okay, in this eight we'll get at least one for a 2 marks or 3 marks. We'll get one question, the image formation, that is from the convex mirror and concave mirrors. So in case if you have any doubt, so please ask me, and read the sign convention properly. So by heart this, so not by heart, just you understand this concept. No, don't by heart. Okay, if you by it you may forgot. So but you understand the concept clearly, and here remember the formulas. So by practicing, by writing and writing, you may remember this. Okay, so in case if you have any doubt, so please message me. Okay, so the remaining thing we'll see in the next class, that is we're going to study the problems in the physics in the next class. Okay, okay, then we'll see the next video. And also write these points in the physics points book. Okay, what you're going to write, so write this okay, write this one, image formation by convex mirrors. So write this, and also write the sign conventions, write the heading sign conventions and write these points. Okay, after that mirror formula and magnification, write that, and also height and this one, magnification formula. So write these things in your physics points book. Okay, uh, after that if you have any doubts, so please ask me. Okay, then we'll see the next video. Have a nice day, take care.